So picture this. You are sitting at your desk. Maybe it's incredibly late. The rest of the house is entirely quiet. The glow of your monitor is literally the only light in the room.
Setting the scene, I like it.
Right. And you are deep in the trenches of building this really complex application. You hit a wall with a tricky API integration, so you casually ask a large language model to just spin up a flawless Python script to handle the payload.
And boom.
Boom, it spits out perfect, syntactically beautiful code in under 3 seconds. I mean, it feels like absolute magic. You feel like you are conversing with an unparalleled genius.
Oh, absolutely. It's a crazy feeling.
But then, just out of curiosity, you ask that exact same genius to count the number of R's in the word strawberry.
Oh, no. We all know how this goes.
Right, or you ask it to solve some basic spatial logic puzzle involving like 3 cups and a ball.
Yeah.
And it completely faceplants.
Just fails with supreme, unwavering confidence. Exactly. Confident failure. And you actually start questioning your own sanity. Like, how can a system be so brilliant at complex code syntax and so mind-bogglingly incompetent at basic elementary school counting?
It's the ultimate paradox of modern software development, honestly. Because as humans, we are wired to equate fluent articulation with deep cognition.
Yes, exactly.
We assume that if a system can speak our language fluently, it must possess this underlying human-like reasoning engine. We project intent and logic onto a system that fundamentally operates on a completely different mechanical paradigm.
Which is why today we are just stripping away that illusion completely. We're going to dig straight into the bedrock of what these models actually are.
So necessary right now.
It really is. For you listening, especially if you are a software engineer trying to build robust applications on top of these foundation models, this deep dive is going to map out the exact structural boundaries of your tools.
We're looking at a stack of recent AI architectural white papers, research notes on adversarial testing, developer docs, all the heavy hitters. To uncover the exact limits of LLM reasoning, we are exploring the mechanics of their failures, why their memory only works in one direction, and how their logic can just shatter with the slightest surface change.
And ultimately, how you engineer your way out of these structural traps. Because if you are building enterprise software, you have to stop treating the model as this omniscient brain.
Right.
You have to start treating it as a specialized processor with profound limitations. The literature actually categorizes these as systematic reasoning failures.
Meaning they are bugs.
Exactly. They are not bugs. They are features of the architecture. The models consistently fail at precise counting, tracking spatial states, discrete arithmetic, and negation.
Like, if you ask a model to track an object moving sequentially through different rooms in a text prompt, it just completely loses the thread.
It really does.
So let's break down the mechanics of why that happens. Because it comes down to the fundamental way the model ingests data. An LLM does not see words or letters the way you and I do.
Right. It sees a sequence of tokens.
Yeah, tokens. So with that strawberry counting example, you see a 10-letter word. The model might chop that word into 3 arbitrary linguistic chunks during tokenization, like stro, all, and berry.
It literally has no mechanism to peer inside those baked tokens to count individual characters.
It's blind to them.
Completely. And the architecture is a forward-pass, feed-forward network. It just calculates probabilities to generate the next token in a sequence, and once that token is generated, the state moves forward.
No going back.
No going back. It has no internal scratch pad to hold variables, update them, check them against previous steps. None of that.
I always picture it like a massive, incredibly complex water slide.
Oh, a water slide. Okay, I can see that.
Yeah, because the architecture is designed purely for the water to rush downward. It is entirely built for forward momentum. The system literally has no mechanism to stop halfway down the slide, swim back up a few feet, check a previous calculation, update a tally, and then resume its descent.
It just falls forward.
Exactly.
It just falls. That actually captures the structural constraint perfectly. It lacks the capacity for subtoken processing or dynamic state tracking. It just propagates activations forward through its layers based on the input context.
But wait, let me push back on this water slide idea for a second, because I use these models for math, and sometimes they get it absolutely right.
Sure, they do.
If I give it a basic algebraic equation, it can often solve for x. It can't have seen every single combination of those specific numbers in its training data. So if it has no internal scratch pad, and no algorithmic execution, how is it successfully solving algebra?
So it is executing an incredibly sophisticated form of generalized pattern matching, which we constantly confuse with algorithmic execution.
Wait, so it's just recognizing shapes?
Essentially, yes. When it solves your algebra problem, it isn't applying a discrete mathematical rule like a standard calculator does. It has seen billions of examples of algebraic structures in its training data.
Okay, so it learns the statistical shape of how numbers and operators relate in that specific context.
Exactly. It recognizes the pattern of isolating a variable. But, and this is the kicker, because it is only matching a pattern and not executing a rigid algorithm, as soon as you give it a math problem involving exceptionally large numbers or an unconventional structure it hasn't seen frequently.
Where pattern matching breaks down and it hallucinates the math.
You got it.
So it is essentially faking the algorithm.
Yeah,
It recognizes the shape of the problem, but isn't actually computing the underlying math.
that's right.
And I imagine that exact same forward-moving token-blind architecture is what makes it fail so spectacularly at negation. I mean, I see this in my problems all the time.
Well, the negation problem is huge.
I will write a strict instruction that says, do everything except this one specific thing. And the model will immediately turn around and hyperfixate on the exact thing I told it to avoid.
Yeah, the mechanics of negation reveal a massive blind spot in attention-based neural networks. In human logic, the word not, or except, operates as a complete mathematical inversion.
Right, it flips the truth value of everything that follows it.
But to an LLM's attention mechanism, not is just another token with a relatively low semantic weight. The model allocates its attention based on heavily weighted semantic concepts.
So if your prompt says, do not think of a pink elephant,
The tokens for pink and elephant trigger massive activations across the network's layers. The tiny mathematical weight of the token not simply gets drowned out by the incredibly loud semantic noise of the subject you just introduced.
which means as an engineer, you are playing with fire if you use negative constraints in your system prompts. You are basically highlighting the exact behavior you want to avoid.
Exactly.
And that token blindness, that inability to process discrete logic, it really makes me wonder how it stores the information it actually gets right. Like if it doesn't understand the rules of math or the logic of negation, what is happening under the hood when it successfully recalls a factual piece of information?
Oh, this takes us into some of the most fascinating research in the white papers. It's a phenomenon referred to as the reversal curse.
A reversal curse sounds ominous.
It exposes a massive flaw in how we assume neural networks store knowledge. When a human learns a fact, for instance, A equals B, our brains automatically abstract that into a bidirectional relational node. We intuitively understand that B also equals A.
But large language models fundamentally do not do this.
They do not. Their knowledge is stored strictly as directional token associations.
Let's dive into the math of why that is. Why does it only learn in one direction?
It all comes down to the autoregressive training objective. During the pre-training phase, the model is fed massive sequences of text, and its only job is to predict the next token.
Right. Next token prediction.
So if the training data contains the sentence, Mary Lee Pfeiffer is the mother of Tom Cruise, the model tries to predict Cruise after seeing Tom.
Okay, that makes sense.
The loss function calculates the error of that specific forward prediction, and then backpropagation adjusts the neural weights to strengthen that exact forward pathway. The network is never asked, in that moment, to predict Mary from Tom.
So the loss is never calculated in reverse, meaning the reverse pathway is never optimized.
Precisely.
Here's where it gets really interesting. It is just like knowing the lyrics to a song.
Oh, yeah, good analogy.
Like if I start singing Just a Small Town Girl, your brain immediately fires off the next words, living in a lonely world. The forward pathway is incredibly strong.
Very strong.
But if I ask you to sing the previous line, or even worse, start from the end of the chorus and sing backward word by word, your brain completely short circuits. You don't possess a spatial bidirectional map of the song.
You just have a chronological forward-moving vector of learned associations.
Right.
And that mapping is a precise mirror of the LLM's internal weights. If you prompt the model with, "Who is Tom Cruise's mother?" the vector from Tom back to Mary was never heavily reinforced during training.
So the attention heads struggle to find the connection.
Exactly, and the model might hallucinate or fail completely, even though the forward fact was heavily represented in its training data.
Wait. If the network only learns facts as a one-way street based on next token prediction, are we even dealing with a system that knows facts? Or are we just dealing with a high probability string continuation engine, and we just happen to get lucky that human language patterns sometimes correlate with factual truth?
Wow, you've just articulated the core architectural debate in AI research right now.
Really?
Yes. These models are not relational databases. They don't store isolated nodes of objective truth. They learn the shape of human language around those truths.
The fact is just an emergent byproduct of the statistical probability of the words.
Exactly. This means the model has massive hidden blind spots that depend entirely on the phrasing of your query.
So if you are an engineer building an application that extracts knowledge from an LLM, your prompt engineering completely changes. You aren't just trying to speak clearly, you're actively trying to catch the slipstream of the model's training distribution.
Slipstream, I like that.
You have to reverse engineer how that specific piece of knowledge was likely sequenced on the internet and format your prompt to align with that directional vector.
It requires a completely different mental model of how your queries interact with the system. And honestly, this directional probability-based memory leads directly into the next major vulnerability highlighted in the research.
Which is,
If the model relies on memorizing sequences rather than learning actual rules, what happens when we throw it a curveball? What happens when we ask it to scale those patterns up?
the house of cards collapses. The sources dive heavily into this generalization and fragility. We look at these models passing the bar exam or writing complex code, and we just assume they are robust reasoners.
But the data on length generalization proves otherwise.
Walk us through length generalization. That's the ultimate test of memorization versus actual reasoning, right?
It is. Let's go back to the addition example. A model learns to add three-digit numbers flawlessly. It appears to have mastered the algorithm of addition.
It looks like it really gets it.
But if you prompt that exact same model to add two 15-digit numbers together, its performance plummets. If it truly understood the underlying rule, carry the one, shift the column, the length of the number wouldn't matter.
Because an algorithm scales infinitely.
Right. But it hasn't learned a scalable rule. It learned a localized bound pattern that only holds up within the specific parameter lengths it saw frequently during training.
So it's basically a localized lookup table. It memorized enough specific examples to give the very convincing illusion that it understands the underlying math.
Just an illusion.
But the moment you push the complexity beyond its memorized scope, it shatters. And what is even wilder is how it shatters when you introduce adversarial perturbations.
Adversarial perturbations. This is where the fragility of the vector space becomes incredibly apparent. Researchers can take a complex logic puzzle that a model solves perfectly. They don't change the logic, they don't change the constraints, they just make entirely irrelevant surface changes to the prompt, changes that a human wouldn't even register as meaningful. And the model's performance completely tanks.
Let me make this hyper-specific for the coders listening. Let's say you give the model a Python problem involving array manipulation. You use variables named x, y, and index.
The model crushes it. It writes perfect logic.
But if you take that exact same logic puzzle and simply change the variable names to banana, helicopter, and shoe,
the model suddenly writes garbage code and fails the logic test.
that is wild. Because as an engineer, you know a variable is simply an arbitrary pointer. It holds no intrinsic meaning to the execution of the logic.
Exactly, but to an LLM operating in a high-dimensional vector space, the token banana carries massive multi-dimensional semantic weight. It is deeply associated with training data about recipes, agriculture, and nutrition.
Ah, I see. By injecting that token into a logic problem, you are actively dragging the attention mechanism's vector space away from pure mathematical logic.
And right into a highly semantic, noisy neighborhood.
The attention heads start firing based on the semantic associations of fruit and aviation, and the logical structure of the coding problem just gets completely drowned out.
It gets completely lost.
Think about the implications of that for a production environment. How do you build a robust, enterprise-grade application if your foundational reasoning engine is this sensitive to noise? Like, if a user inputting a slightly weird word into a chat interface can derail the entire logical flow of your back-end process.
It forces us to entirely reevaluate how we benchmark these systems. We have standard tests where models appear to reason through complex scenarios, but adversarial perturbations prove that the model is often just recognizing a familiar shape in the prompt.
So it's relying on the semantic gravity of the words to pull it toward the right answer rather than actually computing the spin.
Yes, it is advanced pattern matching masquerading as cognitive deduction.
Okay, so let's tally this up. We are working with a system that has no internal scratch pad, it cannot track internal states, fails at negation, learns facts on a strictly one-way street, fakes its knowledge of algorithms, and completely collapses if you rename a variable to a tropical fruit.
That's the summary, yeah.
It is incredibly clear that just waiting for the next generation of models, just throwing more GPUs and compute at the problem, isn't going to fix this.
The white papers are incredibly explicit about this point. We have been living in the scale is all you need paradigm for years now. The assumption was that if we just add more parameters and train on more data, true emergent reasoning will eventually unlock itself.
All right.
But the architectural limits we were discussing, the tokenization, the forward-pass feed-forward design, the autoregressive training, these are structural. A larger model just becomes a vastly more confident, vastly more expansive pattern matcher.
It does not become a more rigorous thinker.
Exactly.
So how do we actually fix this? If
Yeah.
scale isn't the answer, what is the path forward for the engineers listening right now?
It means your job is evolving.
Which means your job is completely safe.
Oh, very safe. You are no longer just writing prompts. You have to build structural scaffolding around the model. The sources point directly to specific architectural solutions: tool augmentation, neurosymbolic approaches, and closed-loop verification frameworks.
This is the critical pivot. You have to leverage the LLM for what it is brilliant at: parsing messy, ambiguous human language and acting as a universal translation layer.
Yes, and you have to actively shield it from what it is terrible at: discrete logic, math, and state tracking. This is the core of the neurosymbolic approach.
Let's talk about how you actually build that guardrail.
Huh.
Tool augmentation is massive right now. Frameworks like LangChain or custom routing agents are exactly what we are talking about.
Right.
Instead of asking the LLM to calculate a discount on a shopping cart, which we know it will hallucinate, you give the LLM access to a deterministic tool. You design a system where the LLM parses the user's messy input, identifies the math operations required, extracts the relevant numbers, and then formats a rigid JSON payload.
And that payload is sent to a standard deterministic Python function that actually executes the math.
Exactly. The Python script returns the exact answer, and the LLM translates that answer back into natural language for the user.
You are marrying the probabilistic flexibility of a neural network with the rigid, absolute reliability of symbolic code. The model never touches the actual math. It only routes the intent.
And this extends far beyond just calculators, right?
Oh, absolutely.
Right.
If you need the model to reason about a schedule or check inventory, you don't ask it to imagine a calendar in its hidden layers. You have it write a database query, execute the query against your real backend, and feed the deterministic results back into the context window.
It's about designing a closed-loop verification system. You never blindly trust the forward pass.
No.
If the LLM generates a block of SQL or Python code, you don't just pipe that directly to production. You route it through a compiler or run it against a suite of unit tests. If the test fails, you capture the error message, feed it back into the LLM automatically, and force it to correct its own syntax based on the hard constraints of the compiler.
So the model's output is constantly checked against reality.
Right.
This redefines software engineering in the AI era. It is systems architecture at a higher level of abstraction. You have to deeply understand the exact boundary where the model's probabilistic capabilities end and where your deterministic logic must take over.
The LLM is the creative engine, the linguistic router, but your code provides the steering wheel, the brakes, and the map.
I love that framework. It's incredibly empowering.
It really is. It means we aren't just sitting back hoping the black box doesn't hallucinate our enterprise data. We are actively engineering the space between its brilliance and its incompetence. And honestly, managing the constraints of your hardware and dependencies is exactly what software engineering has always been.
We just have a much weirder, much more fascinating dependency now.
Seriously, the constraints dictate the architecture. Once you understand the constraints, the illusion of magic fades and the real engineering begins.
Perfectly said.
Which perfectly wraps up our module on reasoning. We have stripped away the magic, explored the mechanical failures of the token architecture, and laid out the blueprint for building robust scaffolding.
And our next focus shifts the paradigm entirely. We are moving from the internal mechanics of how models fail to reason to how they are beginning to interact dynamically with the external world.
That is going to be incredibly practical. We are diving deep into the architecture of agents. We'll be looking at advanced tool use, the intricacies of retrieval augmented generation, and the rapidly expanding landscape of AI systems that are browsing the web, executing multi-step tasks.
And making decisions in external environments, it is essential architecture for anyone building the next generation of applications.
I can't wait.
But before we sign off, I want to leave you with one final thought to mull over as you spin up your code editors tonight.
Let's hear it.
We have spent this entire deep dive deconstructing how these foundation models do not truly reason. They rely on probability, localized pattern matching, and directional memory. They fail fundamentally at basic logic under the hood.
They really do.
And yet, they still manage to write incredibly complex software, pass medical boards, and hold deeply compelling, nuanced conversations.
Wait, where are you going with this?
If a system that is fundamentally incapable of true reasoning can simulate human intellect so convincingly, what does that imply about how much of our own daily human reasoning is actually just advanced biological pattern matching?
Oh, wow. Are we all just predicting our own next tokens?
Makes you think, right?
That is deeply unsettling, but an absolutely perfect place to leave it. We'll see you on the next deep dive. Keep building, keep questioning, and remember, the magic is an illusion, but the code is real.